In this lab, we will be using a device called a polarimeter to calculate rotations of an unknown substance. Here's how it works. Light is first polarized, which allows light in only one oscillating plane to be used. The polarized light passes through the polarimeter, which contains our substance of interest. We then measure the observed rotation of the polarized light through the substance. We can then compare this observed rotation with the expected amount of rotation for this substance, which is called the specific rotation.
Okay, in order to understand this experiment, it's important to understand these equations on the board here, which are used in polarimetry. This value right here is the observed rotation. It is the observed rotation of polarized light that we will use this polarimeter to measure. This value here will give us that alpha value. This value is, this bracketed alpha is the specific rotation, which is an experimentally determined value. So every compound has a specific determined amount of rotation of polarized light that's specific to the compound. C is the concentration, and L is the path length. And the units on these are important. The units in this equation for concentration are grams per 100 milliliters, which equals grams per deciliter. And the units on the path length are decimeters. We're just going to manipulate this a little bit. We won't show you how, but this equation can become more useful by eliminating the 100s here and there to get this bottom equation where this is our observed rotation. That's the number that's coming off the polarimeter. This is the value we're trying to find for our unknown compound. The concentration now is in grams per milliliter, and the length is still in decimeters. It just becomes a more useful equation for this experiment. Okay, so in order to define this relationship between concentration and observed rotation and specific rotation, we're going to need to make a best fit line in Excel, which what we're going to do is we're going to measure the observed rotation with the polarimeter of our unknown solution at differing concentrations. In order to do that, we need to make solutions of different concentrations, and you can do that using this really useful equation called the dilution equation. You'll see this equation a lot as you go forward in chemistry. It's very, very useful. And what it describes is it describes the concentration and volume between two differing solutions of different concentrations and volumes. So we have, our stock solution is a 0.1 grams per milliliter solution. And we want to make 15 milliliters of different concentrations. We're going to start with 0.1, but go to 0.08 and 0.06 and downward to 0 in order to observe that relationship, that linear relationship. We want to make a 0.08 grams per milliliter solution. We want to make 15 milliliters of that from our stock 0.1 grams per milliliter solution. So we're solving for this volume. How much of this original solution do we need to make this diluted solution? So C2 is 0.08 grams per milliliter, and our volume that we want is 15 milliliters. The concentration we have is 0.1 grams per milliliter, and we need to know V1, so we're solving for V1. So V1 equals 0.08 grams per milliliter. 15 milliliters over 0.1 grams per milliliter. That equals 12 milliliters. So we know we need 12 milliliters of this concentrated solution, and to get 15 milliliters, we'll add water up to 15 milliliters.
Here we are zeroing out the polarimeter. The tube is filled with distilled water. After zeroing, we start with the lowest concentration of our solution and measure the rotation.
column for our concentration and a column for our observed rotation. So now we're going to create a graph. Okay, and we're going to add a trend line. And I'm going to display my equation so I can find the specific rotation for our data. Okay, so this equation tells us that we didn't have a perfect data set because we have a b, and ideally you don't want to have it, it's supposed to be 0. But we know that y equals mx, and we can correlate that with this equation with alpha equals bracket alpha CL, where this alpha is our observed rotation. The bracket alpha is the slope corresponding to this equation. And the C is the concentration here, and the L is the path length, which is 1 decimeter. And most of them are 1 decimeter for easy calculation. So here, if you look at our equation, our M value is 50.371. And if you pull up the lab, we can see that there's 2 that lie in the 50 in the glucose and lactose. And for unknown number 4, it's supposed to be lactose. So you can see we're a little off, but we're still close enough that we can say it's lactose.